Swayam Prabha. Digital India. Educated India.
Now, we will move on to the second example. In the second example, we are interested in solving a truss problem. What we want is, we want to design the truss so that it will take the load P, that is, the members of the truss are fixed. You want to find what is the maximum load P that can be applied, so that the members do not fail, and there is a restriction on displacement of this point C. The restriction is, I want this C to be displaced by less than 0.15 mm. Okay. I want this C to be displaced by less than 0.15 mm, and I want to find what is the maximum load that can be applied, so that this serviceability condition on displacement of C as well as the strength requirements of the members AB, BC and AC are met. Okay. Now, we will solve for the member forces first, find which of these member forces is in tension, which of these members are in compression. Then we have to limit the compressive stress so that it does not exceed all the critical load for this member, okay. And then it should also ensure that the material strength is not exceeded in compression, okay. And then in tension also, the material strength should not exceed for the given load, okay. So, let us go about systematically solving this problem. First task is to find the member forces. So, I will use method of joints to find the member forces. First, I will look at joint B. I am looking at joint B, wherein there are two members coming at the joint. I assume the tensile force acting on these members as positive. So, this will be F BA and this will be F BC, okay. And I have a load P acting vertically downward, P by 2 acting like that. Let me assume a coordinate system to be x and y like that, oriented like that, okay. Now, I want to write the equilibrium of forces. I want to write the horizontal equilibrium of forces F x equal to 0, assuming the force acting in this direction as positive, okay. So, this angle would be theta from the figure, and this angle also would be theta, okay. So, horizontal force for member AB would be acting opposite to the positive direction of x, assume positive direction of the force. So, it will be minus F BA into cos theta plus F BC into cos theta, okay, into cos theta plus P by 2 must be equal to 0. This is the horizontal force equilibrium statement. Similarly, I have a vertical force equilibrium. I am assuming the upward acting force as positive equal to 0. Here all the forces are acting in the negative y direction. So, all will be negative. So, I will have minus F BA sin theta plus F BC sin theta plus P must be equal to 0, okay. For this cos theta is, for this cos theta would be 3 by 5 and sin theta would be 4 by 5, okay, where 0.5 is this length of the hypotenuse, this length would be 0.5. From Pythagoras theorem you can get that, okay. So, that will be 0.5 and hence cos theta is 3 by 5 and sin theta is 4 by 5, okay. So, substituting that in here and solving for FAB and FBC, what we will get is, we will get FBA to be minus 5P by 24 and FBC would be minus 25P by 24, okay. What does the negative sign indicate? It indicates that member A, B and B, C are in compression, okay. So, that is what it indicates, okay. Similarly, let me solve for the member force AC by looking at joint C. I am going to look at joint C now. Okay. In joint C I have FBC, again I am assuming tensile forces are positive, FAC, I will have a reaction force VB there, okay, or VC there, I will have reaction force VC there, okay. Now I will write the horizontal force equilibrium first, Fx equal to 0, writing the horizontal force equilibrium, this angle is theta, okay. So what I have is, I have F AC with a negative sign minus F BC cos theta must be equal to 0, okay. This implies F AC is 25 p by 24 to cos theta is 3 by 5. So, that will be 5 p by 8, okay. And then I can find VC by writing the vertical force equilibrium, which is not necessary in this problem. So, I will not do that, okay. So, what is the maximum, what are the member forces? Member forces are minus 25 p by 24, minus 5 p by 24 and 5 p by 8. So, what is the maximum compressive stress, compressive force? Maximum compressive force is minus 25 p by 24, okay, in member BC, okay. Now, what is the allowable compressive force? Allowable compressive force would be minimum of your Euler buckling load, it is a pin-pinned truss, is a pin-pinned structure. So, it will be pi square E I divided by L square, and the material strength, which is sigma y, the yield stress value in uniaxial extension, uniaxial this thing multiplied by area of the cross section, okay. For our case it is given as, in our case it is given as a circular section, it is a circular section of diameter 15 mm made of material with Young's modulus 200 and uniaxial yield stress of 250 MPa, okay, 250 MPa. So, this will be a minimum of pi square 200 into 10 power 3 MPa for E into pi into d power 4 divided by 64 for I, okay, divided by L square for member BC. We found that it is of length 0.5 meters. We found that the member BC is of length same as member AB, which is 0.5 meters, okay. So, that will be, I have to use in millimeters. So, that will be 500 whole cube whole square, okay, okay, comma sigma y is 250 into pi into d square by 4. I have to find the minimum of these two, which is nothing but, if I evaluate it, it will be minimum of 19.6 and 44.1, which is 19.6 kilonewtons. This is in kilonewtons, okay, 19.6 kilonewtons. So, what should I do? I have to limit this 25 P by 24 to be 19.6 kilonewtons, which will imply that P should be less than or equal to that. So, P should be less than or equal to 18.8 kilonewton, 18.8 kilonewtons. Okay. Now, I know the maximum tensile forces in member AC, which is 5 P by 8, and allowable tensile force would be sigma y to area of cross section, which will be 44.1 kilonewtons. This will imply that P should be less than or equal to 8 into 44.1 divided by 5, which will be 70.6 kilonewtons. Clearly, this is not the governing case, 18.8 kilonewtons is the governing case, but you have one more restriction that the deflection at C must be less than 0.15. Now, to find the deflection of C, to find the deflection of this point, this member is a horizontal member. So, whatever this member elongates will be the displacement of the point C. So, you are interested in finding the elongation of member AC. Okay. So, what is the elongation of member AC given a force? We saw that in a previous lecture when we did axial members. So, delta AC would be the stress in the member AC divided by area of AC, okay, into divided by the Young's modulus of AC would give me the strain in that member into the length of AC will give me how much the member has elongated. So, this has to be less than or equal to 0.15 mm. Okay. I know FAC is 5 P by 8, I know area of AC is pi 15 square by 4, okay. Length of AC is 600 mm, okay, because it was 0.3 plus 0.3 it is 600 mm divided by Young's modulus, this 200 into 10 power 3 MPa. Okay, I am using all the units in millimeters. So, I have to use MPa for the Young's modulus. This has to be less than or equal to 0.15 mm. Okay. So, this will tell us that this will give us that P has to be lesser than or equal to 14.1 kilonewtons. Okay. So, give us P has to be lesser than 14.1 kilonewtons. So, combining all the three cases, what we have, P must be less than or equal to 14.1 to satisfy serviceability, or they recommend that the displacement of C has to be lesser than a particular value, and it has to be less than or equal to 18.8 kilonewtons to satisfy strength requirements. Okay. Hence, the allowable value of P allowable, which is what we are interested in finding, is 14.1 kilonewtons. Okay. So, this structure will fail by serviceability requirements if it is going to fail rather than by strength requirements. Okay. This is the P allowable. Okay. So, what you have seen in this lecture is two problems, one 3-dimensional stress analysis problem and one a simple 1-dimensional stress analysis problem, and we saw how to find what is the maximum load that can be applied and maximum stress that can be applied on the structure to satisfy strength requirements as well as serviceability requirements as well as the stability requirements. Okay. So, I hope this gives you a overall feel of what you will be doing in your design courses in the future semesters that you will be taking. Okay. To summarize, in this course what we have seen is 4 concepts: force, displacement, stress and strain, and you have seen 4 concepts which relates these 4 equations that relates these 4 concepts. Basically your stress strain relationship, your called constitutive relation, your force stress relationship which is given by the equilibrium equations, your strain displacement relationship and compatibility condition. Okay. And then you solve some simple boundary value problems like an axial member, a beam bending problem, inflation of a pressure vessel and torsion problem to estimate the stresses. And then we saw failure theories. Basically we saw Tresca criteria, von Mises criteria for ductile failure or pressure hydrostatic pressure independent failure. Okay. And we saw Rankine criteria and Moore-Coulomb criteria for hydrostatic pressure dependent or brittle failures, and we saw how to limit the maximum stresses or the maximum displacements to ensure the safety of the structure. Okay. Thank you.